Welcome back to our heat transfer class, where we are delving deeper into the complex phenomenon of convection heat transfer. This video was made with the support of InnoEnergy. In the first lesson, we have seen the physical phenomenon, the different types of convection, the velocity boundary layer, and the thermal boundary layer. And we asked ourselves the following question. If we don't use computational fluid mechanics, how can we evaluate the rate of heat transfer? Let's see what Newton's law tells us. In this second part, we will study what the convection coefficient is. How is it calculated? What are the typical values? And what is the range of applicability of the formulas to calculate it? Newton's law states that the heat flux at the surface of a solid is proportional to the temperature difference between this surface and the fluid. The proportionality coefficient, H, is called the convection coefficient. Let us now look for a definition of the convection coefficient. On a flat plate in a laminar regime, the heat flux is given by Fourier's law. Equating this expression to Newton's law, we arrive at a definition of the local convection coefficient, which is the product of the thermal conductivity of the fluid times the derivative of the thermal gradient over the plate and divided by the temperature difference between the plate and the fluid. Thanks to this concept of conduction through the thermal boundary layer, we can keep in mind the idea that the thicker the boundary layer, the slower the heat transfer rate. And, therefore, if we apply Newton's law, the lower the convection coefficient. On the other hand, in a turbulent regime, in which the laminar sublayer is very thin and there is mixing in the advection zone, heat transfer, and, therefore, the convection coefficient is higher. It is also observed that in a turbulent regime, the decrease of the local convection coefficient with the distance to the origin is more moderate. We are going to delve into the calculation of the convection coefficients in different flow configurations. The first thing to do would be to find experimental values. For example, what will be the coefficient of convection on an electrically heated flat plate? Using a potentiometer, we regulate the electrical power consumed. If the plate is perfectly insulated, this power, transformed into heat, is transferred to the fluid by convection. By measuring the temperature of the surface and the temperature of the fluid, and applying Newton's law, we will obtain experimental values of the convection coefficient. As the convection coefficient depends on the velocity of the fluid and its properties, we must carry out experiments with different operating conditions. The first thing we notice is that what we can measure are not local coefficients, but an average value of the convection coefficient for the entire plate. And the second thing we can observe is that we will obtain different values of the coefficient depending on how the fluid circulates over the solid and what its properties are. So it will be different for plates than for ducts. And different depending on the fluid, for example, air or water. How to avoid having a different formula for each fluid? The answer is by grouping properties and parameters into dimensionless numbers. The Prandtl number includes properties of viscous friction, energy storage, and thermal conduction. To characterize fluid flow, instead of velocity, we can use the Reynolds number. Now we need a dimensionless number related to the convection coefficient. This is the Nusselt number, which for forced convection is a function of the Reynolds number and the Prandtl number. To get a single correlation or formula valid for all fluids within a range of properties, the Nusselt number is divided by the Prandtl number raised to a certain power. This formula, however, will depend on the type of convection, flow regime, geometry, etc., giving rise to a family of formulas. Another important aspect in the formulas to find the Nusselt number is the temperature at which the properties of the fluid are calculated, since they change with temperature. To calculate the convection coefficient or the Nusselt number, we have an extensive map of formulas. Depending on whether there is a phase change or not, whether the convection is forced, free, or mixed, whether the flow regime is laminar, turbulent, or transitional, whether the flow is external or internal. If it is external, of the flow direction, for example parallel or perpendicular to the surface. And finally, it depends on the geometry of the solid. In this course, we will study forced convection without phase change, with turbulent regime inside ducts. Let's see what typical values the convection coefficient can take. You should keep this table in mind when you make convection calculation problems. The convection coefficients for condensation and boiling are much higher. It is observed that the coefficients are greater for forced convection than for free convection, and higher for liquids than for gases. Last but not least is the range of applicability of the formulas. The first range is the Prandtl number. This number relates the hydrodynamic boundary layer thickness to the thermal boundary layer thickness, being 1 when both layers are equal. The formulas that we will use are not valid for liquid metals with very low Prandtl numbers, nor for very viscous organic liquids. The other range of applicability refers to the Reynolds number, which determines the flow regime, with different formulas for the laminar regime and for the turbulent regime. But we will see all this in detail when we study convection inside ducts.